Okay, so we're all getting recorded and you should be seeing my screen. And there's a PowerPoint I'll be using for texting. And here's this, and let's go here actually. So I've updated the syllabus. Hopefully it'll open right up. There it is. So this is what you have out there. This is the lecture we're working on today. Next week, as I told you, we're going to cover this chapter 4, which maybe John has already discussed, but I'm going to use that as an introduction to some hydropathy papers, specifically this Kite and Doolittle. I may mention these others depending upon how the time goes and how I arrange this when I do it. And then the following weeks, we'll start doing the thermodynamics chapters from Van Hold. There's already an assignment out there from today. So you should already, I think, maybe not. Oh, yeah, there it is. Assignment 3 is already there under today's lecture. Okay, and so let's bury that. All right. So what we're doing today is an introduction to statistics. And I have a kind of a set of notes that I hand wrote, and that's how I usually present this in class for some time now. And so we're going to talk about many of those topics. Many of those topics are discussed in this chapter 1 out of Bevington, which is also posted out there. Okay. But the topics that we're going to be, let's come over here. The topics that we're going to be discussing today are basically noise. It doesn't want to write, pen. Noise. Okay, what we mean by noise. This will have something to do with instrument noise. So it will call instrument noise. Okay. And it has to do with something we'll call experimental noise. And we'll talk about the nature of the noise. And specifically, we want to know if the noise is random or if the noise is systematic. Okay, and this is sort of discussed in this chapter over here, where it introduces, let's make that a little smaller. It introduces the concept of error, which is what I had written up here. It may let me switch back and forth here. The difference between an observed or a calculated value. Okay, and the true value. All right, and the issue, of course, is what's true, because we don't really know what true is. We know what we observe. And so part of this is that the observation is sort of what we trust, and then we try to relate that to truth. Sometimes we can make calculations that seem to be based on theory, and so we could call that the expected value, or we could say it's the true value, but we don't entirely know. Okay, and so part of this is trying to relate experimental measurements with some true value, all right, or some what we think is fundamental observation that we can interpret as a true value. Okay. What do we got here? I see it expands. Okay. So part of the issue is when you're doing this, notice this term here, illegitimate values, which I think the text tries to describe as mistakes or blunders or some kind of an error that occurs. This is what I would often call systematic noise. It has to do with maybe a bias in the data due to something you did, or a bias in the data, something that the instrument did. And you generally want to try to get rid of that systematic noise. For example, a good example of this is a baseline, where the raised baseline is sort of added into all the data, and the baseline has some other origin. So for example, if you have light going through pen again. If you have light going through a cuvette, okay, and the path of the light is such that it actually passes through the bottom of the cuvette where there's sort of solid glass. Okay, so you don't have the cuvette pushed all the way in. Usually cuvettes have some kind of a wall and some kind of a bottom. Okay, and the solution is what you see here. But if you actually hit the bottom, then you will have some kind of scattered light from that, and it will impinge away from the photomultiplier. There's the photomultiplier looking at what's happening. Okay, that might be prone towards a systematic error. If the beam isn't parallel to the spectrophotometer and it strikes the walls, then you would get scattered light from the walls, and those also would deflect away from the photomultiplier, and you would have this sort of raised baseline effect in the data. So that could be a possible origin of that. What we're looking for is a signal that has none of these systematics in it. There are often ways of correcting that. Okay. The first topic that we sort of want to talk about has to do with accuracy and precision. And I'll jump back and forth here between a couple of sources. So what you would like to know is how accurate and how precise your data is. Now, accurate gets back to this idea of truthful. Accurate means that it's close to what it should be, close to what is expected for the system. Precise refers to how big the uncertainty is, or how big the scatter is in the data, regardless of whether it's accurate or not. All right, and so this chapter displays this in two ways. The data on the left is presumably not accurate because it's off the line. The line here is meant to be the truth. Okay, that's what we expect. We get points that are off the line, so they're not accurate. But notice the uncertainty or the error bars are very small. So the data is very precise, it's just getting the wrong answer. As opposed to on the right, where the data is close to the line, so it's accurate, but the error bars are large, so they're not very precise. So ideally what you want is precision and accuracy, and that depends a little bit on how you collect data. Okay, let me see. Okay. So let me switch back over here to do this. So when you collect data, let's go down a slide here. When you collect data, you usually make a certain number of measurements. And what I mean by that is the light that is impinging on, let's say, a photomultiplier from a spectrophotometer, and it's going through a cuvette. You're collecting data for some period of time. Okay, and so if you were to be plotting this as sort of a chart recorder, you would have some kind of measurement occurring. Okay, and if you were scanning wavelength while you were doing this, okay, then you would have some kind of a measurement that might be occurring. It might be going down with wavelength, it might be going up with a wavelength. But in any one of these regions, it's actually signal averaging over with some time constant. Okay, so it might be collecting data with a time constant of 1 second. And so it's collecting signal over some time constant. So it's scanning at such a rate that it allows you to get an average value. Okay. Now, you don't always, or you aren't always aware of this. Okay. But you're basically getting some kind of a mean value. And that mean value is often determined by some sum over a whole series of values, which we'll call x sub I. But you're making those measurements and then you're averaging them over some time. Now, in this case that I've described, the instrument is doing this. But if I were to simply make a measurement at some point, let's say I just wanted to sit and let's redraw this so it has a peak in it of some kind. And I just want to sit at one place and make a measurement, then I might signal average at one point and then I would have some average value. And the average value would depend upon how many times I made the measurements and how many measurements I collected, and then it would give you some kind of an average. Okay, so we would call this, usually we would call this a mean value. Okay, if you were to do this again and again and again and again, then you would get some kind of a measure of what that X is, averaged so many times, and you might get a distribution that comes out of that. And this is what the distribution might look like. It may be broad, it may be very narrow. Okay, it depends on what the system is that you're measuring. All right, and so this is how you make some kind of an average value, and it gives you some idea of what the uncertainty is in the data. That would be what the width is, and then what the signal is at that point, which ends up being your mean value. Okay. And so the distribution about this is what we're sort of interested in. We're interested in knowing if this is a distribution that obeys certain kinds of properties. All right. Now, if I were to draw this in a slightly different way, let me erase some stuff here. If I were to draw this in a slightly different way, let's draw this so it actually has a skew to it. Okay. And so when you make these measurements, whatever they are, this is what you get. Okay. And so now the average value is something different. You plug it into this formula, you'll get some value that's an average value. Okay. And so we would call this the mean. All right. Another calculation that you've probably heard of is something called the median. And that would be the point where half of the data points are above and half of the data points are below. Okay, and so as I've drawn this, the median might be a little bit different. Okay, and so let's call it that. All right. And then there would be something that is what's called the most, my notes say it's a mode. I think there's another way of describing this. It would be the most probable, and the most probable would be the biggest point, because in terms of the statistics of this, each of these values is a probability. And so that would be the most probable point. Okay, and so that would be the main mode is one way of describing it, or most probable is another way of describing it. Okay, and so what we're looking for are distributions that look sort of randomly distributed. Ideally, you want to have a certain sort of shape. Okay, now the value that I originally drew here had sort of a symmetry to it. Okay, and it had a symmetry where it had a certain width that was equal on both sides. So there was a mean, and there was what we will now call a standard deviation about this. And the standard deviation is often defined as some kind of a difference between the data and the mean value. And it's usually defined as the square, so that the values that are smaller and bigger all lead to positive values over the sum. And so you square the difference between the mean value and all of the individual points. The individual points would be these points along the data that you collected. And we would refer to this as the standard deviation. It's often called the sigma value or standard deviation. Okay. Very often, this value is also called the standard error. When I change, it wants me to activate the pen again. And the standard error usually is divided by a slightly different number because the points are all linked to one another, and they think that not every point is independent of one another. Okay, but it's basically the same kind of a calculation. The sum of the squares of the differences, or what we will eventually also call the residuals. Okay. This is where we are. Okay. Now, these data basically define this type of a distribution. And one of the things that we're sort of interested in is knowing something about these distributions, what their properties are, so that it tells us something about the quality of the data that we're collecting. All right. And so this is what we're sort of interested in. Now, ideally, what we would like is for the data to be symmetric and what we call Gaussian. Okay, and we would like the data to be evenly distributed about some average value. Okay, and so the Gaussian nature of it is sort of what we're often interested in. Okay, and the Gaussian nature usually gives you the impression that the data is randomly distributed about some average value. Okay, if you have other kinds of noise or other kinds of characteristics, then you can begin to suspect that something else might be going on in the data, or there just may be something odd about the system that you're working on. Okay, so let me describe two other parameters that come up in this sort of thing, and I'll make room right here for this. Sometimes your distribution is skewed the way that I just showed you. And sometimes the skew is towards the low side. And sometimes the skew is towards the high side. Okay. And so this usually has a meaning. And the meaning is the skew with a negative value. So it's skewed to the low side, or a positive value, it's skewed to the high side. Okay, the skew actually has a definition. It's this 1 over n, and it's a sum over x sub I minus x mean cubed. Okay, and so you notice that when you do this, the negative value being cubed could give you in principle negative values. Okay, and so that's why you can have negative and positive values to the skew. And then I'm going to introduce another idea now that I could have introduced up here, and I'm going to call this a weighting factor. And this has something to do with the uncertainty of every individual point. If all your data is equally weighted, then these all average out and can be ignored. But they might be weighted differently because this point, for example, is less noisy than that point and less noisy than this point, and et cetera. So each point may have a different amount of noise on it that makes up this particular shape. And so you want the data to be weighted by that weighting factor. Okay, generally speaking, people don't have that in their data sets. But if you're signal averaging in a way that you can record the deviation, then you can get this. Okay. Another parameter that is often described for data sets is something called the kurtosis. And the kurtosis has something to do with the shape of the distribution. And often distributions, let's see if I can do this there. Distributions can be peaked. They can be broadened or they could be peaked. Okay, and so the kurtosis also has a definition, and it's 1 over n times the sum of x sub I minus the mean over the weight to the 4th power minus 3. Okay, And so this gives you some indication of the fact that your data deviates from being Gaussian. All right, you can usually see it in the data. You can usually see that the skew is fairly easy to see. Hyper sharp, maybe not always so obvious. This broadened or flattened thing can be often visible. There are sort of expected values for this. If a Gaussian distribution is tested for skew, you usually expect it to be less than 6 over the number of measurements, okay? And if the kurtosis, the Gaussian kurtosis should be less than 24 over the number of measurements, okay? So anything larger than this gives you an indication that it really is a skewed distribution, or it really is a distribution that exhibits flatness, okay? Part of the issue here is the magnitude of n, okay? So often when you make measurements, the magnitude of n is small. So most of you guys are doing experiments maybe that involve cell culture, involve certain kinds of parameters that you're measuring involving cells, and you don't necessarily have that many measurements. You might have triplicates, okay? Maybe you have 5s, maybe you have animals and you have as many as 7 animals, okay? These are really small numbers, all right? When I do measurements, I tend to have much bigger measurements, okay? And so this is an example of a data set I'm working on right now. And you can see distributions here. And you can see these distributions have fair amounts of points. This is the number of points. So that this distribution has peaks around 20, but you can see it has closer to 300 data points. This one has 200 data points. You can see it has counts up to 35. Okay, so when I divide by n in examples like this, these become significant distributions. You can see they sort of look Gaussian. This one may be really sharp. This one may have some broadness. It may have a little bit of flatness and kurtosis. I haven't made a measurement on this yet, okay? But I could make a measurement on this and get a sense of, are these widely distributed? They sort of look Gaussian to me, and they have specific standard deviations that have been calculated. So you can see what those standard deviations are for the different distributions. Okay, let me get the, all right, rid of that. Okay. So what we're looking for in these kinds of measurements are distributions that are generally randomly distributed, that we can calculate some kind of a mean, and we can get some kind of a measure of the precision and maybe the accuracy, presumably, of the data that we're going to be measuring. So we would like to know something about the statistics of the measurements that we're going to be making. Okay. Now, Gaussian has a certain meaning. Gaussian has a certain meaning, and I'm going to give you a formula right now that we'll come back to later. So a Gaussian distribution, and let's write this up here again, usually means that there's a certain probability. That's the standard deviation. There's a square root of 2 pi in the parameter. And then there's going to be an exponential over which we have 1/2 times the data points minus the mean over some standard deviation, all squared. Yes. Okay. And so this is basically the formula for what a Gaussian distribution looks like. And so if you were to plug in a value of sigma and a value of mean, and then you generated data points with this kind of a formula, you would generate something that has this Gaussian shape to it. This kind of, the drawing that I make is never as perfect as it should be, but it will basically have something that is very symmetric looking, okay, with a certain width, all right, and a certain mean, okay. The place that this often gets assigned has to do with the fact that the standard deviation is often a measure of what fraction of the area under the curve is included here. Okay, and so one standard deviation often means that you've reconnected 68% of the points. Okay, and so if this was a standard deviation, then that would mean that that area, and my drawings are going to be ugly, but the area under one standard deviation would capture 68% of the points. Two standard deviations would usually capture something like 95% of the points, and three standard deviations would capture something like 99.9% of the points. So if you increase the magnitude of the standard deviations away from the mean, then you would capture more of the area under the curve and you would capture more of the points. So most of you are probably familiar with this simple calculation. It was shown back here in our formulas here, I guess. No, it was the one before. Nope, the one before. Standard deviation here, where we were capturing the difference from the mean squared summed over all the values. Okay, and so that's the kind of measurement that you would generally calculate. Often we do these in spreadsheets in ways that you just click on it and you ask it to give you the statistics. That's the formula that it's going to use. Okay, and so this is the kind of measurement that we often sort of make. All right, now the standard deviation that you get, as I explained to you a second ago, often depends a little bit, the accuracy of it depends a little bit on how much data you've collected. If you do a single measurement, then obviously you can't take an average. But if you do multiple measurements, then usually the standard deviation goes as the square root of 1 over n. Okay, so if you make 2 measurements, then it goes as the square root of 1/2. If you make 4 measurements, then it goes as the square root of 4. If you make 9 measurements, it goes as the square root of 1 over 9, etc. So you can improve the quality of your measurement depending upon how many times you average. Okay, and so you can trust the standard deviation a little more. All right, now that doesn't mean that you won't have systematics in the measurements. You might, for example, make a measurement 3 times and then have a pipetting error while you're doing it. Okay, but generally speaking, the noise will improve as you make more and more measurements. There's a limit. This doesn't improve infinitely. Okay, there's no such thing as 1 over infinity here. Eventually you run into what I'll call the instrumental noise. Okay, and eventually you can't do any better than what the instrument itself can do. Okay, but generally speaking, you take more and more points to improve the quality of the standard deviation of the data. Okay, so I like to often flash a laser to catch data at least 4 times, but if I'm going to make something more than 4, I go to 9. And I do it because it's a factor of 2 or a factor of 3. And I sort of like to do it in sort of whole numbers. So if I'm going to flash a laser multiple times, it's 4 or 9. Okay, generally speaking. If you're doing pipetting, it's not always easy to kind of make 4 measurements or 9 measurements or 16 measurements, etc. But within certain experimental techniques, you can do this. Okay, and so this is what you sort of expect from improved measurements. Okay. And then the other thing that we need to take into account is I've already stressed the fact that we're talking about, and let me come back over here now. We're talking about what I anticipate is sort of Gaussian. All right, and I'm going to scroll down here to, we're talking about things that we sort of expect to have a Gaussian sort of shape to it. Okay, and so what you have in this figure is a demonstration of what I just referred to a little while ago. The data that you collect might be sort of boxy. All right, and the boxiness of the data reflects how many data points you collected, but the fact that you don't have so much data that you get a smooth curve. You always get something that's a little bit ragged. In this figure that I showed you a second ago, you can see even with hundreds of points, it has a certain raggedness to it, okay? You have to get up into the thousands and thousands of points to generate something that really looks smooth, all right? So then when you fit this data to an equation that describes a Gaussian pattern, and so it's this equation that I showed you right here for fitting the data, then you'll generate some kind of a curve, all right? And so that curve is what we take to mean the truth, all right? That's sort of what we think the truth is. And in this particular example, it comes back with a mean of 19.9 down here and a standard deviation of 0.52. But what the legend is claiming is that this is only an approximation to the truth. It's an estimation of the truth. It's your measurement, okay? It's what we would call a sample distribution, but it's not necessarily the parent distribution. And I think they use the term parent distribution down here, right here. Okay, does my pen work on here? Yes, it does. Well, almost does. Parent distribution versus sample distribution. Okay, here. All right. And all it means is that that's your estimate. But the statistics behind all of this is always acting as though there's some truth out there. And the truth here, I think, is represented by the dashed or dotted line here. Okay, simply telling you that if you were to repeat this over and over and over and over, they would all sum to give you some real parent truthful distribution. There's, of course, really no such thing. It's a construct. It's a mathematical construct to help you sort of understand it. But nonetheless, this is what you sort of get. There are other kinds of distributions that are shown that might give you unusual means and modes. I actually did this manually rather than do it here on this figure, but it's the same ideas. So when you go back and look at this, you'll see that I stole the ideas. Okay. I'm looking for a figure down here that I think is here. Maybe it's not here. It's not in this chapter. Okay. It's in another chapter. So I'm going to go back over here and do this manually. There are other kinds of distributions that are out there. Okay, and one of the kinds of distributions that you often get is something called a Poisson distribution. This is usually a counting distribution. So if you are measuring, I know most of us don't measure radioactive counts anymore, but if you were doing some kind of a counting distribution, then you would get some kind of a distribution, but the distribution often bangs up against the zero axis, because you start out with small amounts of counts, and then you can essentially get zero counts for some of your measurements. Okay. And so a Poisson distribution often has this unusual shape to it. It will collapse to a Gaussian distribution as the average gets bigger and bigger, or as the mean gets bigger and bigger. And eventually it will look like a Gaussian distribution. But for small counts, it will have this shape that is very close to the ordinate, very close to the axis. And so it will have an unusual shape. Okay. So for Poisson counting, as you want to increase the precision or the standard deviation of the measurement, then you basically just collect more counts. And in Poisson distributions, the standard deviation goes essentially as the square root of the mean, because this gives you increasing amounts of counts to get a bigger and bigger mean. And so it ends up being a measure of the standard deviation of the measurement. Okay, again, most of you are probably not doing counting data, but it's something that ends up talking about. The other kind of distribution that textbooks talk about are something called Lorenzian distributions. And Lorenzian distributions are usually described as resonance frequencies. They have a unusual shape in that they sort of start up and then they peak and then they have this broadness to them. So they have this unusual broadness to them on the tails. And it's usually a measure of energy or energy cross-section that is being measured in some kind of a spectroscopic measurement. Okay, you generally will not see this in most of the measurements that you and I are going to make. One example is absorption of radiation. Biophysically, these are usually a certain class of measurements that we'll get to later on in the class. Okay. Let me come back over here and let me bury this. All right. So, all right. So let me do one more thing here before I move on to chapter 3. There's another way of thinking about Gaussian. Okay, so Gaussian distributions, so let me start again, also fall into a class known as binomial distributions. Okay, and it has some kind of a predictive value. They generally predict something about a particular distribution of points or the kind of data, how data is distributed. And it overlaps with what a Gaussian distribution looks like. Let me introduce it in a slightly different way, though. Let me tell you about something called Pascal's triangle. Does anybody know what Pascal's triangle is? I know you're all muted, but I'll assume the answer is no. Okay, Pascal's triangle is this. It's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc. So you can see all I'm doing is I'm summing points. That 1 goes to the outside, but 1 and 1 is 2. 1 and 3, 1 and 2 is 3. 1 and 3 is 4, etc. Okay? This distribution that I'm drawing, if you were to plot it, looks Gaussian, or it looks what we call binomial. So what does binomial mean? Binomial means that you have some kind of a parameter. Let's say it's A plus B raised to the 0th power. Okay, this would give you a value of 1. Let's do A plus B raised to the 1st power. Okay, this would give you a value that involves a coefficient of 1 and 1, because this raised to the 1st power basically gives you the value of 1. This raised to the 1st power basically gives you A plus B. A plus B squared gives you A squared plus 2AB plus B squared. 1, 2, 1. There they are. 1, 2, 1. And so as you go down this equation and you expand to the 3rd power and the 4th power and the 5th power, and you want to know what the coefficients are, the coefficients are 1, 3, 1 and 1, 4, 6, 4, 1, etc. Okay, and so that's why this is known as a binomial distribution, because the coefficients can be written down in this way. Okay, coefficients can be written down in this way because they match what is in the Pascal triangle. A Pascal triangle is effectively a reflection of this form of distribution. Okay. So this is sort of a mathematical trick, a mathematical game. And people have been working on Pascal triangles and using them to kind of predict behavior for hundreds of years in the field of mathematics, in the field of astronomy, etc. Okay. So again, this actually relates back to Gaussian. All right. So if I wanted to write out the coefficients that are obeyed by this sort of equation, then I would write them out another way. And that other way has to do with something called n choose k. Okay. And so n choose k involves an n divided by a k, written usually in this way. And what it means is n factorial over k factorial over n minus k factorial. Okay. And so presumably you know that n factorial means n times n minus 1 times n minus 2 to 1. Okay, so it's the entire multiplication back to 1. All right. So if I write 6, 3, then this means 6 factorial over 3 factorial, 6 minus 3 factorial. All right. And then you can write these numbers out and solve the problem. You have a factorial button on your calculator, by the way. Okay, so it's 3 times 2 times 1, and that's 3. So it's 3 times 2 times 1. Okay, so this 2 cancels this 2. This 3 turns that into a 2. This 2 cancels that 2. This 3 cancels this 3. And so you get an answer that looks like 20. Okay. If I go back to this table, if I draw one more 1, 6, 15, 20, 15, 6, 1, that's the 20 that I just calculated. That would be the central point in Pascal's triangle that would be predicted in the binomial expansion if I wrote this out to the 6th power, and I would end up with 20. Notice this is the 3rd power, the 4th power, the 5th power, the 6th power. This is the 6th power in the 6 choose 3. That would mean the 6th power in the binomial, and it would be that central term that would give me a 10. Okay, so these things are all connected and related to one another. I'm going to jump.
Dr. Correa?
Yes.
Why you pick number 3? Like why is 6 to 3 but not 6 to 2 or
you
6
could
to
choose 6 to 2. If you choose 6 to 2, then you would get 6 factorial, 2 factorial, 6 minus 2 factorial. So you would get 6, 5, 4, 3, 2, 1 over 2 times 1 over 4 times 3 times 2 times 1. So you would get a different set of numbers. The 2 would cancel the 2. The 2 would cancel the 6, give me a 3. The 3 would cancel the 3. The 4 would cancel the 4. 3 times 5 is 15. There's the 15.
But it's not in the central.
No, it's not, because it's not the central point. It's the second point. If I do 6, 4, sorry. This is a way of calculating all of them. 6, 4, this would be 6 factorial, 4 factorial, 6 minus 4 factorial, but this would be 4 and 2. It would give me the same value, and that same value would be this one. This one. And then if I put in a 1 or a 5, I would get 6. So it predicts all of them. Okay.
Okay.
All right. And so there's a big connection between all of these different relationships. All right. Let me do one more thing. And this is jumping way ahead. This is jumping ahead more than a couple of weeks. All right. Let's say I have a molecule. Pen. I have a molecule, but it has 4 binding sites. Okay, 4 binding sites. I want to know how many different ways can I bind one ligand to one site. Okay, and so the answer is that I can bind it here or here or here or here. And so there are 4 ways to bind one ligand to 4 sites, but only once. How many ways are there to bind no ligands? Well, there's only one way because it's the empty site. And so that would give me a 4. How many ways are there to bind 2 ligands? Okay, and so you can bind 2 ligands, one here and here, or here and here, or here and here, or here and here. And if you do all of the math, you'll find that there are 6 ways.
Oh.
And how many ways can I bind 3 ligands? Well, there's basically how many ways can I have an empty site and 3 full? And so there would be 4 ways. This is the empty, this is the empty, this is the empty, this is the empty. That's a 4. And how many different ways are there to bind all 4 ligands at the same time? There's only one way to do that. Okay, so no ligands, 1 ligand, 2 ligands, 3 ligands, 4 ligands.
Oh, okay. I see.
1, 4, 6, 1, 4, 6, 4, 1. It's this right here, that column right there.
Yeah.
Or that row. All right.
Okay.
And so the connection here is that we're interested in Gaussian noise. The connection here is that we have this mathematical tool that mathematicians started playing with. It had to do with choices. Okay, it had to do with choosing things, choosing options. You're trying to predict something and you're trying to guess what the right answer is. But what you're doing is you're choosing statistical choices. And so there are multiple ways of choosing. Okay, imagine in the 1500s when somebody was playing with this, maybe they were already rolling dice. Maybe they were already playing cards. Okay. Maybe there was somebody who actually had a cup hidden under which was some kind of a coin, and there were multiple cups, and you were trying to guess what was underneath. In other words, imagine people were gambling. All right. Then you would start making logical choices, and the way you made those logical choices was by applying statistical concepts. I have this many choices, and these are the options that exist. And when I choose something, I've not chosen something else. How many other things have I not chosen? What's the probability that I'm going to be right? Okay. And so it's sort of maximizing the probability. So that's exactly what these ideas are. This is sort of the probabilities of doing things depending upon how many choices there are. This is the coefficients in a binomial expansion, but look, it gives you exactly the same coefficients. And then when you start looking at this from the perspective of ligands binding to a protein, then you suddenly have the same distribution of binding sites or options for filling binding sites. Okay, later on, when we derive all of this in terms of binding, we'll get down to the fact that when there are 6 ways of binding 2 ligands, that means that it increases the chance of binding by a factor of 6, because the overall affinity is the same at each one of those choices, but there are 6 choices. So it increases your overall probability by what we will call later a statistical factor. How many different ways are there to have 2? Multiply by 6 times the overall affinity, and that's the effective affinity that you're actually going to get because of the fact that there's more ensembles of them. All right?
Yeah, thank you.
The other place that I usually apply this has to do with when we're sitting in a classroom. All right. So there are 7 of you. Okay, so there are 7 of you. That's probably not the way I'm going to do it. There are 7 of you. And if we were sitting in a classroom with 10 seats, then how many ways can 7 students sit in 10 seats? And the answer would be this. Okay, I'm not going to calculate it out, but it would give you the number of options for the statistical probability that 7 students will sit in any given arrangement. There's a whole series of arrangements, and allowing each of you to sit anywhere you want, you will get those, but this is what you would end up getting, how many different arrangements there are. 10 seats, 7 students, here's the probability. If there were 7 seats and 7 students, obviously there's 1. And then everything else has to do with what the different options and the different choices are. Okay, as again, this is often called choose the ways or N choose K. And that's another example of how you might use this and why you might need this. Okay, so that's meant as sort of an introduction to the idea for how you would think about data and how you would think about probability. Okay, you want your data to be sort of randomly distributed. You want to know that there's no systematic in your data. You would like to know that things are not wrong in some way, shape, or form. Okay, now let's switch gears to this chapter that has to do with error analysis. Okay, so the chapter that is here, and let's make this a little bigger maybe, and I'll go back and forth on this. The data that's here begins thinking about ways of propagating uncertainty when you have measurements that are due to multiple parameters. So in this case, they begin with X and they begin with a function of U and V. Okay, and what this derivation is essentially doing, it's trying to get you to recognize that if the outcome is a function, the outcome is a function of U and V, okay, then the value that you get for the distribution or the uncertainty will be a function of the mean value of U times the change in X with respect to U, and the mean value of V times some kind of a change in X with V. So X depends on U and V. And as you make measurements involving U and measurements involving V, you get measurements involving X, and they are deviating from the mean value based upon some kind of a dependency, some kind of a how X varies with U and how X varies with V. Okay, is this going to let me scroll a little bit? Yes. Okay. The thing is that there's also a correlation between U and V to one another. And so you might have an error in U that affects V and an error in V that affects U. And so there would be this thing that's often called a covariance. It involves the uncertainty in U, the uncertainty in V, and the error in X with respect to U, the error in X with respect to V. And this covariance is another term that you sort of have to take into account. We generally assume that covariances cancel out and they don't impact one another. Okay. It wants to shrink on me and make it more difficult. Okay. And so the way that we generally talk about this is to get away from the linear terms and talk about this in terms of the square terms, because we would like to avoid negative and positive values canceling out perfectly. We would like it to be a sum over squares. So we would like it to have the appearance of what I already called a residual, okay? And so the general equation that you can write down for this sort of thing looks like this. It involves the error in what it is you're trying to measure. Squared will be some function of the error squared in U and the error squared in V, and then a covariance term that for the most part we're going to ignore. And this will depend upon the change in X with respect to U squared and the change in the X with respect to V squared, okay? And so it can be summarized usually or truncated usually by neglecting these covariance terms in this way. This is what is referred to as a propagation error, okay? It's the error propagation equation, okay? And it's the general way that you can calculate it. All right, let me come over here. All right, so we're going to do this now, and I'm going to follow the flow of the chapter, but I'm just going to do an example, okay? So if we had something that was a function of U and V, that's the terminology we were just using there. And I'm going to make measurements, but what I'm doing actually is calculating X based upon the value of U and V. For example, if X is U times V, okay, I want to know what the error in X is squared. And so I can tell you that this is going to involve the error in U squared times the partial of X with respect to U squared plus the error in V squared times the partial of X with respect to V squared, okay? So I need some mean value with a standard deviation for U and some mean value with a standard deviation of V, and then I need this connector. All right, so this is an assumption now. If you haven't had calculus, probably I should have asked that when we were all facing one another so you could raise or not raise your hand. This is where you're going to get a little bit lost. If you've had calculus, and I think you all have had calculus, the partial of X with respect to U is V. Because when you take the partial of X with respect to U, this is the partial of U times V with respect to U. And there's only one U, and that cancels. And so you get V. The partial of X with respect to V, and you get V, you get V squared, excuse me. Partial of X with respect to V, it's the partial of UV with respect to V. U is not V, so it's a constant. You cancel out the V and you get U, so this is U squared. So this X squared standard deviation is U squared times V squared plus V squared times U squared. All right. Now notice X is U times V. So if I divide by U squared V squared all along here, U squared V squared, U squared V squared, the V's cancel, the U's cancel, the V's, I'm sorry, I'm supposed to cancel this one and this one, not that one. So what I end up with is U squared plus V, U squared plus V squared over V squared. So I canceled the wrong thing here. Okay, the V squared, the U squared, and I get this. This is essentially X over X squared, because x is uv. So the error over the value of x is the relative error. The term here is the relative error. The sigma is the absolute error. In other words, in the units of whatever x is. And these are u over u squared plus uv over v squared. So the square of the relative error is equal to the sum of the squares of the relative errors of u and v. Yes? Or the relative error, this is going to be tiny, is equal to the square root of the sum of the squares of the relative errors, v over v squared. So if I just take the square root of both sides, this one becomes the relative error is equal to the sum of the squares of the relative errors. Okay, this is sort of a general idea and a general concept that you get in all of these propagations. Okay, so the idea here is that you can use this kind of formula for all kinds of specific examples. Okay, and to apply this, you essentially need to have errors or uncertainties for particular kinds of examples. And so this particular example here, suppose, wait, let's go back. This is an example in that chapter, and it's showing a measurement of so many counts with an uncertainty. And then it's showing you what the relative error looks like. And the relative error would be the uncertainty of 26 counts divided by the mean value. And so it gives you a relative error of 0.038 or a relative error. So I'm talking right here in the middle. The data that this is coming from is up above here. And it gives you a relative error of 0.038 or 3.8%. Okay. And so that's one of the values of expressing stuff in terms of relative error or relative uncertainty, that it gives it to you in a percent. When I know what the number is, however, I really have to report the absolute error. I really have to know that 708 really has an uncertainty of 26.9. It does not have an uncertainty of 3.8%, although you could write it as 3.8%. You would just have to make sure you indicate percent. Okay. And so you would need to make sure that you know what the units are, or you would have to make sure you express it as percent. You would not express it as 0.038 because that's a different kind of unit. All right. And so this method of doing this is a reflection of applying this equation. All right. Now, the values that I just gave you, the equation that I just gave you, is expressed here. There we go. This is, it's not letting me go up or down. Why is it not letting me go up or down? Yeah, it's expressed here as multiplication, and this is the example that I just did, except now the multiplication involves coefficients. Is that right? Okay. So here, sorry, let me go back up to be clear for you. This is the value that we're talking about right here. X is equal to AUV. And there can be a sign, so they were trying to generalize. So over here, A UV. So X is equal to AUV, and they put a sign in front. Okay, so the partial of X with respect to U, the U is removed and you get AV. The partial of X with respect to, oh, that's a typo. That should be a V right there. That should be a V. All right, and then you get BU because the V cancels out. Okay, and so the equation looks like this. You get the relative error of X squared is equal to the relative error, excuse me. There, this is sort of being derived here. Let me re-derive this the way. So this jumped a step because it's back on the previous page. Okay, so this jumped a step. Partial of X with respect to U squared. So this is the step that they jump, they skip here. And that I just went over. Okay. And they then convert it to the relative errors by dividing all of these terms by X, plugging in this value and then dividing by X, and X is AUV. Okay. And so you cancel all the terms, and then we're going to neglect the covariance term, and we're going to get some kind of a value. All right, and so they apply this to this example here involving a triangle and a measurement involving B times the base times the height divided by 2. So the area of a triangle is the base times the height divided by 2. Okay, and so that's the formula there. And then you take the various equations and plug them in, and you get an equation that looks like this. So this is the area in the error in the area times the error in the base squared, partial of area with respect to base squared, plus the error in the height squared, partial of area with respect to height squared. Okay, so it's the first one is going to be H over 2, and the second one is going to be B over 2, and then you divide both sides by A squared, and then these are all squared. I'm sorry, these are all squared. And then when you divide by the area and rearrange, that's the equation you're going to get. And you'll notice that those involve relative errors, but depending upon what you know about the system, you can make a measurement and you can plug numbers in. So you can see that the measurements involve a base of 5, a height of 10, divided by 2 is an area of 25. The error in the base was 0.1. The error in the height was 0.3. So there's the 0.1 and there's the 0.3. And then these are being normalized by the actual base and the actual height. So it's being divided by 5 squared and 10 squared. And you plug this all in and you end up with an error. So the error ends up being 25 plus and minus 0.81. So the uncertainty in all of the parameters will propagate and give you the propagated error. Okay, so let's do something just to think about this. 0.1 over 5 is the error in the base. 0.3 over 10 is the error in the height. 0.81 over 25 is the error in the area. Okay. So if you do this yourself, but I'm going to do it here while I'm sitting here. So 0.1 divided by 5, okay, is 2%. 0.02. 0.3 divided by 10 is 0.03 or 3%. Okay. 0.81 divided by 25 is 0.324 or 3.24%. So part of the point here is that the error in one parameter is 2%. The error in another parameter is 3%. When you multiply them together, divide by 2, you get a larger error because the error in each parameter actually doesn't cancel one another out. They actually enhance. They actually can become a bigger number in uncertainty. So the uncertainty in this is 2. The uncertainty in this is 3%. Excuse me. But the uncertainty in the product is larger. The point of error propagation is that the uncertainty will grow when you do some kind of a mathematical manipulation with the numbers that you have. Okay. And so what this chapter is doing is showing you different kinds of calculations that you can do, different formulas that you can make this kind of a correction on. Let's do one more together. Imagine that it's a quotient, U divided by V, okay? The error propagation formula is this. Error in U, partial of X with respect to U squared, plus the error in V squared, partial of X with respect to V squared. This is the general error propagation. We're neglecting the covariance term. So what's the partial of X with respect to U? This is a constant divided by V because these aren't U, there's only this U. And so it's A over U. What's the error with respect to V? This value is actually AU times V to the -1. So the partial of that with respect to V is AU, the minus sign comes down, and this becomes V to the -2, okay? If you take, let me do this over here on the side. If you take the partial with respect to X squared with respect to X, this is 2X. If you take the partial with respect to X cubed, it's 3X squared, etc. The value comes down, but then it decreases by a value of 1, okay? So this value is AU over V squared. So this formula becomes partial of X with respect to U is A over V squared. Partial of X with respect to V is AU over V squared squared. Okay. That looks messy. If I divide by X, AU over V squared. So if I divide by X squared, this is now the square of the relative error. So if I divide by AU over V squared, okay, notice that we have an AV squared and it will cancel. And I'll just get sigma squared over u squared. And then if I do the same thing here, AU over V squared, okay, notice I get a u squared that cancels. And what I have here is an a squared V to the fourth divided by a squared V squared. Notice the a squares cancel and the V squared cancels this forward to a square. So what I get here is sigma x over x squared is equal to sigma u over u squared. And what I get here is sigma v. All that's left is v squared over v squared. If I take the square root of both sides, this square goes away. And so sigma x over x, the relative error, is equal to the square root of the sum of the squares of the relative errors. Okay. If you go back here, I showed right here in a product, the relative error in x is equal to the square root of the sum of the squares of the relative errors. I've run out of screens. Oh, maybe we've lost. Pen, there we go. There's my pen. X equals a product, or if X equals a quotient, the error in X is equal to the square root of the sum of the squares of the relative errors. Either one of these gives the same result. Okay. Okay. So this chapter gives you other equations and other formulas. Okay. I'm not going to go through all of these. I've already taken enough time, I think, with that. It includes things like exponentials. It includes things like logarithms. This will require you to know, okay, that the partial of e to the x with respect to x is e to the x. Okay. And the logarithm, this is the powers formula that I already wrote down for you. This has to do with the partial of x. It's using a b here for some reason. Is b times x to the b minus 1. And logarithms, the partial of the logarithm of x with respect to x is 1 over x. Okay, so you'll need to do some reviewing to get that down. Okay, so the assignment that I gave you is to do these examples. Okay, so this is one of the questions. basically show me what the uncertainty is given these formulas. And there's a misunderstanding here. When it says X is 1/2 U plus V, that's sort of the way it's written here, or U minus V. This means this. Okay, the 2 and the U and the V are in the common denominator, all right? It's not just 1/2 times U plus V, which is just linear. That's not what it is. This is what it is. And so it's 1/2 times U minus V in this one right here, okay? All right. So what you can tell from this group of calculations is there's a whole summary of what the formulas look like for various examples. Not all examples reduce to perfect examples, and so some of these may not actually reduce down to simple algebra. A couple of them reduce down very nicely. Okay. Let's do one more topic. And the other topic has to do with least squares and fitting data to a straight line. And it's relatable to what we're doing here. So they give you a data set, and then they show you examples of fits of the data to various equations. And the example basically is that you're fitting it to the equation for a straight line. And the equation for the straight line is a plus bx. Okay, and so the question is how do you give the best approximate slope and intercept for data? And one of the examples is to use what is referred to as least squares, where you have some variation between the guess and the actual data. And so the guess is the formula. The guess is the formula and the actual data. And so when you fit the data, you come up with an intercept and a slope times the X values, and that gives you some estimate of Y, and you can take a difference between the actual value and the estimate from the equation, and you generate essentially a residual. And so what you want to do is maximize or minimize the magnitude of the residuals. You want to minimize the size of the residuals, okay? And so you basically would like the line and the data to be the closest that it can be. And one way of doing this, let me make this a little bit bigger. One way of doing this is imagine that you are trying to get residuals that obey some kind of a Gaussian distribution about the line. All right, and so you would like it to obey an equation like this, where the residuals correspond to this term, the actual data and the equation, squared, plugged into this exponential, and then averaged about the line. Okay, this would be a way of getting what those residuals look like. Let me show you one thing here. These data are about the line. Let's do this one. It's a little bit, is it going to drag? It's not going to drag. There. No. These data are about the line, okay? But each one of these has a distance from the line, okay? And so one way of looking at these data, and this is a way that we often look at data later. I'll show you this in a second. There's a figure right here behind, I'll show you. And basically what it is the error. It's the yi minus whatever the y minus whatever the y0 is. And you basically end up with residuals, and they get distributed about some central point involving X or some distance, okay? And they will be distributed about, and so what these points correspond to is how far is it from that point or that point or that point to the line, squared. and it will look Gaussian. And so that's what you're trying to do. You're trying to fit the data so that it's the closest to the line, closest to a straight line when you do the fit, okay? And so you're essentially using the Gaussian equation to do this, all right? Now, what that means is, where it says y minus yx, it means you're actually comparing the experimental point with the equation for a straight line. And so it's y sub I minus a minus bx, because the equation is the equation for a straight line, all right? So if I subtract the data point minus the fit prediction, that gives me the magnitude of the deviation, and squaring that gives me the residual. Now, what the technique of minimum least squares does is it minimizes this parameter called chi. Chi is this equation, which is basically the sum of the residuals squared. They're often corrected for some kind of a weighting factor, which for our purposes we can ignore, okay? And so we have some function called chi, and it is now going to be a function of a and b. This is the definition of the chi squared, chi squared, okay? And it's a function of the intercept and the slope. So we want to minimize that, okay? And so similar to what we were doing before, we can minimize this by taking a derivative of chi with respect to a, and it's a chi squared, and a derivative of chi with respect to b. And then so this is what we were going to be minimizing, all right? I'm pausing because I want to show you something so that I haven't gotten too far ahead of myself, okay? When I'm writing on a board, maybe I'm more organized. I have too many tools in front of me right now. I'm minimizing by taking a derivative and setting it equal to 0, okay? Let me erase all of this. Okay. Imagine I have a function. And the function is 3x to the 4th minus 8x to the cubed minus 6x squared plus 24x. And if I plotted this function out for you, it would actually look something like this, okay? So I'm going to take the derivative of this with respect to x. And I'm going to get 12x cubed. The 4 comes down, leaving a 3. I'm going to get 24x squared. I'm going to get 12x, and I'm going to get 24. Okay. And what I'm going to do is I'm going to set this equal to 0. All right. And what I'm going to show you is that you can, and usually when people show you this kind of stuff, we've chosen it to be perfect. So if we reduce this to 12 times x cubed minus 2x squared minus x plus 2 is equal to 0. So I'm going to factor out a 12. And then plucked out of a hat, I'm going to show you that this is the equivalent of this. And what you could now tell me is that the solution to this problem is minus 1, 1, 2. Minus 1, 1, 2. And this derivative, which is the slope, goes to 0 at these 3 points. And that's approximately right. Okay. But if I hadn't plotted it for you, you wouldn't know that this was a minima and that was a maxima and this was a minima. To determine that if it's a minima or a maxima, you usually take the second derivative, which is called the curvature. And when you do that on this line right here, you get 12 times 3x squared minus 4x minus 1. Okay. And now the question is, what is the value of the curvature at x equals 1? And if you plug numbers in here, you will see that it's a negative value. And if you plug minus 1 in here, you will see that it's a plus value. And if you plug 2 in here, you will see that it's a negative value. Okay. So this is 3 minus 4 minus 1, negative. This is 3 plus 4 plus 1, positive. Or is it minus? Well, it's minus 1 because there's no x. Okay, and this is 12 minus 8 minus 1, which is positive. Oh, I said it's negative. It's positive. Okay. So the curvature tells you who's a minima and who's a maxima. This point at minus 1, this is a minus 1, sorry. This point is a minus 1 is curving up. So it's a positive curvature. This point at 2 is curving up. So it's a positive curvature. It's a minima, a minima. This point is curving down. It's negative. Okay. So you can learn something about the minima and the maxima and the curvature in the data by taking derivatives of the data. Okay. Now, this is sort of plucked out of the air. It's a review of calculus. It's sort of a review of physics, but this is what you can use the mathematics for. All right. That's what this is doing. We are looking for the minima by taking the derivative with respect to the parameter A, the intercept, and setting it equal to 0. We're taking the derivative of the sum of the differences of the chi-squared, of the residuals, excuse me, with respect to the slope and setting it equal to 0. And this is why we're setting it equal to 0, because we're looking for a minimum value that predicts the best fit. All right. So once you set this equal to 0, you can rearrange these equations, and you now have two simultaneous equations. This equal to 0 and this equal to 0, and they're rewritten right here. Okay. And then what you do is you rearrange. So you bring these parameters on the left and some of the parameters on the right. And now what you have is simultaneous equations involving y and xy and x squared, etc. Okay. So these simultaneous equations now can be solved for A and B that will give us a unique solution to the problem. Okay. Now, solving simultaneous equations can be done. In this particular case, you could do this sort of mathematically and rearrange these equations to do it. What this chapter shows you is that you actually would do this by some kind of a matrix technique. And that matrix techniques involve each of these coefficients. Notice these coefficients here are the coefficients that are in this equation. Okay, it's this sum, 1 over sigma, y, etc. They're all reflected in the way that we've written all of this down. And then this series of matrix approximations will give you a solution to the problem. Now, again, this is sort of jumping into something that's beyond what you do, or maybe what you know. How many of you have ever had linear algebra? Any shaking heads? No linear algebra, is that right? One linear algebra. Okay. So these are the types of ways that you would do it. Now, how would you actually do this? Well, you would put it into some kind of spreadsheet and click fit to a linear equation, and it would report back a minimum. It would report back the best fit with a slope and an intercept. Okay. It would actually use these formulas. It would actually use these formulas to get A and B. Okay. This series of sum all of the x's squared, sum all the y's, multiply them together, sum all the x's, sum all the x times y's, multiply them together, take the difference, divide by this determinant value down below, and it would give you the value of A. So in your calculator or in your spreadsheet, this is actually written down. Okay, this is actually already there. Okay, and it just simply plugs the data in, the X, Y data in to give you the best fit. All right. It even allows you to calculate uncertainties in the individual values for A and B. It actually has formulas for calculating those uncertainties for A and the uncertainty for B. And so the uncertainty in A and B is also a formula that sort of gets plugged in. Okay. Now, this is what this chapter calls linear least squares. Okay, and it sort of summarizes this in a couple of different ways here. The next chapter in this book is something called nonlinear least squares, or fitting a polynomial, or something like this. But I'm going to now new slide, come down here. Go back to home, and then how do I make the pin show up again? Pin, there it is. The other way that you do this, we have data that we're trying to fit in terms of a straight line, but we might actually have a polynomial. Okay, so there might be bigger forms of equations that you might want to fit. And so how do you go about doing this? And one of the ways that we can often do this is a numerical technique. And the numerical technique involves basically guessing values of A and B, and then looking at the uncertainty in A and B, and then improving the fit in some way. Okay, and so this is what our goal is. Our goal is to get this best fit. But if you actually just plotted something like the intercept and the slope versus one another, you would get some kind of a table of parameters, and you would guess and guess and guess and guess until you got to some value that is the best value in terms of the absolute value that you're looking for. Okay, and you can do this by some kind of a search algorithm, and it would give you a certain value that you can plot in this way. And there would be a best fit that would show up as your best fit. And that wouldn't show up in this plot. That would show up in a plot of, Let's do it here and see if I can do it. That would show up in a plot of RMS versus A and B, and there would be some kind of a surface out here. Okay, and that surface would be reflected here, and it would have a certain height, and you would be looking for the point in that surface that is at a minimum value. And that's the way you would sort of do this numerically. You would sort of guess values and then have some way of saying, aha, if I move A in a certain direction, it gives me a better estimate. And so I'll move in that direction, and I'll move B in another direction. And you move around this A-B space until you find the best value that corresponds to the minimum in this error space. And so the RMS here is usually the Y value minus the Y0 value, and it's usually reflected as a square. Okay, so it's the sum of the residuals, the points versus the line, okay, squared, and you're trying to minimize this RMS by guessing values of A and guessing values of B. So that's what this routine back here is doing. My fit basically here is comparing points, which are the red points, to a best fit, which is the green, and the comparison is the blue. Those are the residuals. And so these are all the parameters down below. This is a much more complicated example, but there are 12 data sets here, all of which reflect some kind of experimental data. The red are the experiments, the green is the fit, the blue is the differences or the residuals. And I'm doing it on 12 different data sets simultaneously. And then way over here, you can see the standard deviation that gives you the best fit. Okay, so let me stop this. So this is jumping way, way ahead. I have experimental data. There's 12 data sets here. You can't see 2 down below. There's a molecular weight. There's some parameters that have something to do with buoyancy terms, the extinction coefficient. And then there's this other parameter that we'll talk about soon involving non-ideality. And then when you start fitting this, you can see that it's going to increment the values down below once it gets going. And it's changing the value a little bit to see if it improves the fit. And so every single one of these cells has an initial concentration. Every single one of these cells has what I call an offset. So all of these are offsets. That basically has to do with where the baseline is. Okay. And so that's what it's doing. It's adjusting 12 offsets. It's adjusting 12 concentrations. And it's asking how well the lines go through the data. Each one of these has a local fit. This one is 0.054, 0.062, 0.057. And then there's a summation over all fits that gives you this standard deviation here on the left. Okay. And so this is literally guessing and changing the parameters. Now, how does it guess? Well, it guesses by having some estimate of what direction would improve the RMS. So what direction of A would improve the RMS and what direction for B would improve the RMS. One of the ways that this is often done is by what's called a simplex method, where you put down, where you put down 3 points and you guess a triangle. And then you ask, is the RMS better here, here, or here? If the RMS is lowest here, okay, excuse me, which is worse? Here, here, or here? If the RMS is worse here, these are 2 better estimates, then you do what you call a reflection and you flip this point to this side, and now these are your 3 points. You've walked in space to improve the quality of the fit. If I have over here 26, 25, 26 points. I do this 26 times and try to improve each one 26 times and then move them all and see what happens. And then check again. Now I have this, this, and this point is now fallen out of the calculation. So it's gone. Hello, there we go. And I do it again. And now this is the worst point. So I reflect that point to the other side, but I do it 26 times. Okay. So this is a very crude introduction to the way that we describe and fit data. All right. So let's go back here. So go here. Let's stop that because it'll steal CPU. Okay, so there's a summary at the bottom here of how you do this. And then the next chapter in this book is linear least squares to a polynomial and how you might go about doing all of that. I'm going to stop sharing. Okay, so what we covered today, go back over here. What we covered today was we had a discussion about noise and the different kinds of noise. We had a discussion about randomness and systematic. We had a discussion about distributions, shapes of distributions, means, medians, modes. We had a discussion about Gaussian and what Gaussian means and what deviations from Gaussian might mean. We had a discussion about a formula for predicting what a Gaussian distribution might look like. And then we discussed a couple of other different kinds of distributions involving Poisson and Lorenzian. I then related Gaussian to Pascal's triangles, to polynomials. I related Gaussian to n choose k and showed you that n choose k has use in terms of statistical opportunities, whether it be people in chairs or ligands binding to sites. Then we propagated errors, and I showed you how to propagate errors. We derived an equation that looks like this, a general polynomial equation that looks like this. And then we looked at certain formulas. I came up with certain kinds of sums that involve square root of the sum of the squares of the residuals. And then I showed you other kinds of formulas. And then we deviated into minima, maxima, taking minima, maxima with respect to parameters, using that to minimize certain kinds of formulas and get solutions to certain kinds of formulas, and then applying that to linear least squares. Okay. This felt a little disjoint to me. You need to read chapter 3 and chapter 6, and you need to do the problems that I've assigned. So I've assigned the problems in chapter 3. Primarily what I'm asking you to do is propagate error, show me what the error equations are for various formulas. And then I give you an example, and the example is two equilibrium constants and a product. And so given this uncertainty in K1 and K2, what's the uncertainty in K3? And given K3 is delta G minus RT ln K3, what's the uncertainty in delta G? Okay. So there's a number of examples here. I think it goes through E, and then there's this problem here. All of this basically has to do with propagation of error. I'm suggesting to you that this is a thing that you primarily are going to need to know how to do experimentally. The introduction to linear least squares is something that's going to come up later. I gave you an introduction to it in the example when we get into certain kinds of data sets and analyzing certain kinds of data sets. This series of data that I showed you down here is from that example where I'm fitting 12 data sets, and then I'm showing you the statistics for individual parameters and how well the statistics are being determined, what their distributions are, and what the statistics are for those individual parameters. Okay, that will all come into play when we discuss this in a couple of weeks. All right. Do we have any questions right now? Cindy had stopped me to explain something about n choose k. Is there anything else that you want to ask me right now?
Oh, Dr. Correa, when you write the exponent, like you write some formula with the exponent and some bracket with the number in there, what does it mean? Which means we raised the number next to the exponent.
So you mean
word.
it's e exponent raised to a
The power-
times u?
Yeah. It's in the chapter.
Yeah. The polynomial that we went to, let's see if I've got that here. Here. So this is an exponential here. This is another way of writing it, right?
Mhm.
And so we could write this down as e raised to the power of -1/2 times x minus u squared, right? But this instead is written as ex with values. All these are calculations that you have to make, right? X is a certain point, u is a mean, that's a weighting factor. Calculate this and raise e to that power. So you could just write e to the x, but x in this case is all of this.
Oh, yeah, I see it. I see it now.
Okay.
Thank you.
All right.
Thank you.
Anyone else? Okay. So some of you hadn't turned in homework yet, and you're putting it now in my mailbox or you're emailing it to me. Okay, so I'll check my mailbox because I think some of you have added stuff to my mailbox. When I collect a full set, I'll grade the first 2 problems. Okay. You now have a third one that's due next week. And there'll be another one for the lecture we give the following week. Are there any questions?
One more question. Yeah, in order to understand this part, you know, like, do you think I need to do a lot of review in derivative and linear algebra? Because since I took calculus for a long time ago, I might.
Well, certainly the derivative stuff that's in the propagation formula, you need to practice your derivatives. So to that level, you need to practice derivatives. When we get into thermodynamics in 2 weeks, we will immediately start doing stuff that is essentially calculus. And so I will be deriving stuff constantly that involves calculus. In principle, when you follow along, you will be learning that. Okay, so I will be teaching that. It would not hurt to do review if you're not familiar with it. A lot of the problems that I give you will involve calculus. So the problem set next week, I don't know exactly what it looks like yet, but I have an idea of what it looks like. There will be some derivatives there and some minimization, setting it equal to 0 kinds of stuff. Okay, and so you'll learn, it will reiterate calculus for you in that process. Appreciate what this course is. This course is basically a series of problem sets, and you will demonstrate ability based upon how well you do in the problem sets. And so if my problem sets reflect what I teach, then you will be learning the material as in terms of applying it to a problem set. Okay. So if you need to practice calculus in the process of doing that, yes. I may try to do something with linear algebra in an example like that, but I generally don't get into that detail because I generally give you software. You do stuff in terms of software that I give you. We're running out of time here, and so I won't show that to you now. I'll show that to you maybe next week. I'll try to implement an example where I show you what it is that you can be doing. You're using what spreadsheet are you using with John? Are you using a spreadsheet software? Are you using GraphPad or not GraphPad? Prism? Are you using Prism with John or no?
He said we will be. He said that we can get a 90-day free trial on our personal computer and that he'll let us know when to download it.
Okay. We usually try to get the university to give that to you, but then we have to fight them to get them to give it to you. We should all have it. I have it on my computer, and I know they gave it to me. I don't use Prism usually. I use something else. All right. John and I will talk about that. In Prism, if you put in XY data, you can do linear fits. You can do exponentials. You can actually fit to a Gaussian and come up with a mean and a standard deviation. Okay, so Prism is one of the ways that people interpret and analyze their data. John likes to use Prism because it also links to enzyme kinetics. And so it also has built into it formulas for enzyme kinetics, formulas taken from the book that he likes to use. And so that's one of the reasons that he likes Prism. And so I guess that's what you'll be using it for once you get through the visualization stuff that he's doing with you now. Okay. Next week, I'll resend the link so we're on the same page. Okay. Talk to you later.
Thank you. Thank you, Dr. Correa.
Thank you,
And
Dr.
I'm
Correa.
going to now stop the recording.